Now we have to rename this compressor. Let us say we write it as compressor. It doesn't take more than 8 letters, so we have to make do with compress. Now we have to write the specification of compressor here. For that we go back to our flow sheet and we find it an isentropic compressor whose discharge pressure at this end should be 10 bar and it will operate at 88% efficiency. So we go back, click on this compressor. What is the model type? Model and type. So model, it will be compressor, not turbine, and type, it will be isentropic. And here we can give various outlet specification such as discharge pressure, pressure increase, pressure ratio, power required, etc. So our specification is discharge pressure, which is 10 bar. So we give 10 bar here. So essentially now although this is complete, but some extra information is given here, 88% efficiency. So although it is complete, but we can give extra information here of 88% efficiency. So we write 0.88. It is isentropic efficiency. If you do not give any information over here, it will take 100% efficiency. So it will be compressed up to 10 bar. So that is the job of a compressor. Now again we perform the simulation with next button. Well, we have to specify the distillation column specification. So what are the specification that we have? Distillation, that will be rigorous calculation. So it will be equilibrium separation. So we keep it equilibrium. There will be 15 stages. So we write here 15, and the condenser will be partial condenser, that is 1.95. Now it is partial vapor because partial condenser may produce either vapor or vapor liquid both. So in our case we have only vapor, we do not have any liquid distillate. So it is vapor, partial vapor. We do not have anything this side. So it is partial vapor. And then we have some more information. The partial condenser will operate at 1.95 bar. So that we will see here. Yes, operating specification, it is still red. So these two information we have to give. Reflux ratio, we have to use 5. So we write 5 over here. And distillate rate, here it is 20 kilomoles per hour. So it is 20 kilomoles per hour. So instead of distillate rate, you can give bottoms rate, reflux rate, boil up ratio, all these things, distillate to feed ratio, condenser duty, but we have the information distillate rate. So either of them if you give, the equation will be complete. So its configuration is complete. Let us go to next. So it is stream. Okay, so stream, it is asking for feed stream. So where the feed stream is fed. So we have the information, it is 8th, feed stage 8. So we write it here 8. And then the next one, pressure. Pressure, condenser pressure, which is 1.95 bar. So we give 1.95 bar. Then it is also complete. Now here there are certain optional terms are there, you can check. I mean, stage 2 pressure or pressure drop in the rest of the column. So these are the information that you could give, but even without them the equations are complete. So we go to next, and here it says run the simulation now. So that simulation environment is complete with all the specification written. So run the simulation now. It simulates with no warnings and no errors. And let us check the results. Here, see the results. We have molar flow rate of 20 kilomoles per hour. That is exactly what we wanted. We wanted 20 kilomoles per hour distillate rate, which exactly it is. But we are interested to know what is the composition of LPG, right? So we go here again and check the individual composition. See what are the composition. Go to mole fraction. So you see, so methane is 0.0495, so it is 4.95. Ethane is 23%. It is 0.2298, so it is 23% ethane, 21.78% propane, 45% N-butane. And you can see the percentage of cyclohexane, benzene and toluene. Toluene is trace amount. Not much of toluene is there. But cyclohexane and benzene, some percentage is there, very, very small. So that is the specification of LPG. So we write here, we rename this thing as LPG. Now we have to do something with this flow. It will go to column 2, and this column 2 is not rigorous calculation. We will do some shortcut calculation. So here, go back to the column. We won't use rat frac, we will use distill. So in this distill, we will use shortcut distillation using Edmister method. So we'll bring in over here. So we go here, reconnect destination at this point. And there will be two material balances, two material outstreams. And here we will give a total condenser. Okay. So this end will be pumped. So we need, you can see, this end will be pumped. So this is the C7 product, toluene product. So we go to the pressure changer, we bring in the pump model over here, and go to reconnect destination and connect with this. So pump is connected. Go to material once again, bring it outside. So this is our C7 product. So we rename them. We rename this with C6 product, and this one is C7 product. Okay. So this is C6 and this is C7. Now we can go to next. It will definitely ask for the specifications of this shortcut distillation, and let us rename this B6 column. We haven't done it yet. Neither did we do it for the rigorous one. So we rename it as, say, shortcut distill method. Dist. So this is our shortcut distillation method, and this one we write as rigorous distillation. Okay, right. So it will ask for the specification of this distillation column and this pump. Okay, so let us press next. Yeah, it is asking for pump. It could ask for the distillation only also, but distillation, as it starts with S, so it comes later. Pump comes first, P comes first, so it is asking for pump specifications. So let us see. Pump pressure increase is 0.5 bar and efficiency is 66.7%. So discharge pressure, well, it doesn't have discharge pressure, it says increase in pressure, so it will be pressure increase. We write it 0.5 bar. Now this much is sufficient, but still we can give the efficiency of the pump, which is 66.7%. So it is 0.667. Let us press next. Yeah, now the distillation column, the specification we have to give. Now it is number of stages, it is 20 stage, and feed stage as 10. So it is 20, feed stage is 10. Reflux ratio, it is 4. Distillate to feed mole ratio, is 0.6, and condenser type is total. The condenser pressure, again, condenser pressure, it is 1.9 bar, reboiler pressure is 2.1 bar. So it is condenser pressure 1.9 and reboiler pressure 2.1. And this is very well known fact that the reboiler will always be at higher pressure than the condenser. So our specifications are done. So it is ready to run the simulation. Again, there is no error and warning. We can check now the output. What is the specification of C7 product? So we can double click. This is the result. Okay. So you see here the molar flow is 29.66. We are interested to know about the mole fraction, so that we can understand the composition of C6 product. Here you see methane and ethane 0, completely nothing is there. Propane, you can call it 0 as well, so as butane. These things are not there at all. Cyclohexane is 37.36% and benzene is 62.54%. So these only constitute the C6 product. So you can understand how it is, because your cyclohexane, it is C6H12 and benzene is C6H6, So that's how you have your C6 product. Now along with that, you can check the C7 product also, because you have already run the simulation for pump as well. Here you see benzene is only 2.13%, cyclohexane is 2.34%, toluene is 95.48. All others are 0. The lighter key components are all 0. So toluene is 95.48%. So it is mainly C7 products. So till now we were discussing about the liquid side of the flash tank. Now we are yet to do with the lightest keys, that is methane, ethane and all. So these things are regarded as the lighter component. We called it the leftover gas. We called it leftover gas. So this leftover gas should be burned in a combustion chamber. So this is a reactor. Basically this is a reactor, and we know that this combustion chamber will be governed by the reaction stoichiometry. So we will have a reactor model that runs on stoichiometric. So for that we have to bring in the reactor. So there are several reactor: yield, stoichiometric, equilibrium, gives free energy, CSTR, plug flow, batch. We will use the stoichiometric reactor. So bring in the stoichiometric reactor over here. We give a name, stoic, keep it here, and this leftover gas should be sent to this reactor. Okay. Now this stoichiometric reactor is not complete without the air, because which is used for burning the fuel, right? So we bring in a material which is feed. This is not very good way of presenting, although there is nothing wrong in it, but we have to make it a bit better so that anybody can understand. Yeah, now this is okay. So this is basically air. This is air, and the outlet is this one. This is outlet, which will go to, sorry, there is an extra one we have to delete. Yeah, now we have to rename it. Let us rename exhaust. So this is our exhaust gas. Okay. Now it will ask for the specifications. Okay. Let us press next. Let us see what it asks. Yeah. Now it is asking the air input. Okay. What is the input specification for air? Now we are stuck with something new, because air doesn't contain either of them. Air contains nitrogen and oxygen, and the exhaust will be mainly CO2 and H2O. But we didn't do it, we didn't include these as a component over there. So we have to include these components as well. So what we should do, we should go back to the property database. Here we have to add a few properties. So we go to component specification once again. Here we write oxygen. It is so conventional, if you write O2, it will take oxygen over here. Similarly, nitrogen, it will take. And then CO2, carbon dioxide, H2O, water. So all four things which are not there, we have brought in. So again we have to run this next so that the binary interactions again can be calculated along with the new components. That we have done. We can safely go back to simulation now. Yes, now you can see the extra components have been added. Now as we know that air contains nitrogen and oxygen 79 and 21%. So nitrogen will be 0.79 mole fraction, and oxygen will be 0.21 mole fraction, which will add up to 1 mole. Temperature, its temperature is 50 degrees centigrade, and the pressure is 10 bar again, and molar flow rate is 1200. Okay, so this is mixed, fine. Now we have to go to the reaction stoichiometric reactor. There let us see what are the informations available. It is a 100% combustion with pressure drop 0, heat duty 0, that is adiabatic, and the pressure is 10 bar. So how we can use this information? Now it doesn't talk about the temperature. Temperature it doesn't talk about, but it necessarily talks about the heat duty, which is 0. And the pressure is 10 bar. So either you can write 10 or 0. If you write 0, then it will be regarded as pressure drop. And if you write 10, then it will be regarded as 10 bar pressure. Now specifications are there. We go to next, reactions. Here you have to add the reaction components. These reactions you have to add in. I will tell how. You have to first say new. Now the reactants, what are the reactants? The first reaction is methane and oxygen that will react to produce carbon dioxide and water. So this is carbon dioxide and water. Now coefficient, 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole carbon dioxide and 2 mole water. Right? And fractional conversion, that is component of CH4, methane, is 1 because it is 100% conversion. Okay, it is 100% conversion. So each and every one fractional conversion, if it is say 60% conversion, then you have to write 0.6 of methane. So we write next. Now it is complete, it is showing it is complete because it really doesn't know whether there is any more reaction going on. So it is showing reaction complete, but you have to give all other 6 reactions which are written over here. You have to add in all the reactions to make it complete. Now one thing is very common for all the reactions, that one of the reactants, that is oxygen, is common for all of them, and the products are also common for all of them. So instead of writing all the equation individually, we can copy and then paste it 7 times. Okay, so this is our reaction 1. Reaction 2, it is not methane, it is ethane, right? Let us say ethane. Reaction 3 will be propane. Reaction 4 will be butane. Reaction 5 will be cyclohexane. Reaction 6 benzene, and reaction 7 toluene. So all of them we have given over here. So each and every one of them we have to edit individually. So this is ethane 2746. 2746 component ethane. Reaction 2, reaction 1 is methane. Reaction 3 propane. So propane, it will have 1 5 3 4. So 1 5 3 and 4 fractional propane. Reaction 4 for cyclohexane, N-butane, 2 13 8 10. 2 13 8 10. Reaction 5 cyclohexane 1966. 1 9 6 and 6 component of cyclohexane. Number 6 benzene 2 15 12 6. 2 15 12 6. And the last reaction is for toluene 1974. 1974. Now all the reactions are given with their stoichiometry. Now everything is complete. Now next, let us run the simulation. Yes. So it is generating the result, no warning, no error. Let us see the result. Exhaust gas. We are interested to know the composition of this gas. So its molar flow is 124266 mole fraction. Now we can see it is 100% conversion, so no methane, no ethane, no propane, no N-butane, no cyclohexane, benzene, etc. Mostly carbon dioxide and water. So it has 4.54% carbon dioxide, water is 6.86%, unreacted oxygen 12.29, and the nitrogen mole fraction is 76.28%. So nitrogen is there without any reaction. If you see the mass fraction or mass flow rate, the role of nitrogen, you will see here. You see nitrogen 26556.8 kg per hour. Okay, compare it with air, original air. What did you send? You send the same amount of nitrogen. So nitrogen remains unreacted. Okay, is an inert component. But oxygen you sent 8000 kg per hour, and unreacted is 4889.77 kg per hour. Rest of the oxygen has reacted. And in air there was no carbon dioxide and water, but in the exhaust you find 2487.7 kg per hour of carbon dioxide that is produced out of the stoichiometric reaction. So this is the complete simulation of the process flow sheet that we have discussed so far. Now, so we have developed a steady state model of the plant. We have verified the material energy balance of the unit operation and unit processes. We have checked the composition of the process streams. We have analyzed the process conditions such as temperature, pressure and flow rates. And now we are left out with doing this stuff, that is perform case studies on changes in the following process condition. First we will decrease the heater temperature and see what happens. Then we will change the discharge pressure of the valve, and also we will change the reflux ratio in the distillation column and see what happens in these three cases. Okay, so let us first go to, now here let us here the temperature was 40 degrees centigrade. Let us decrease it to 30 degrees centigrade and see what happens. Okay, so please note that here the temperature, earlier it was 40 degrees centigrade, now it is 30 degrees centigrade. Now definitely it will affect the flash condition, and because here there is heat duty 0. Okay, so whatever the heat that is coming from here, it will be going through these two streams. Now let us see whether there is any change that happens with these two. So the result in the number 4, we had mole flow of 30.5667. So it is 30.5667. So much of mole of leftover gas is going upwards. Now if we run this simulation with a change from 40 to 30, let us see what happens. Remember, it was 30.5667. Now simulation is run. Now let us check what is the result. So here the result, it is 28.2006. Earlier it was 30.5 something, now it is 28.2. So it necessarily means that if your heater temperature is down, then the less amount of material will be vaporized. Okay, so the per hour mole content of the leftover gas will also reduce to some quantity. Earlier it was 30 point something, now it is 28 point something. So this is the effect of reduction of heater temperature. Now let us go back to our old thing, that is 40 degrees centigrade, and rerun the simulation. And check our calculation. It should again come back to 30. Yes, now it is 30.5667. Now then we have to change the discharge pressure of the valve. Okay. Now let us go to our second one, that is change in discharge pressure of the valve. So discharge pressure of the valve right now it is 2 bar, and it's the outlet the stream 5, its composition, you can see the stream 5, it results in molar liquid fraction is 88.1031%. So if it is compressed to 2 bar, then it is 88.10%. Now if the valve, if the pressure is increased to 5 bar, then obviously the liquid percentage should increase, right? Liquid percentage should increase. Let us see whether it happens that way. So remember, it is 88.10% for 2 bar pressure. Now let us say it is 5 bar, and for 5 bar it should increase from 88% to something. Let us see whether it increases and to what extent it increases. So now we go back and check the valve 5 results. Here you see molar fraction is now 95%. So it increases from 88% to 95% by changing the valve outlet pressure from 2 bar to 5 bar. Okay. Now let us see what is the effect of change in reflux ratio. Now before that, let us do one more thing. Let us change the valve pressure to say 1 bar, that is atmospheric pressure. Okay, let us see what happens. Here we may expect some interesting result. That means we are saying that we will change the valve position in such a way that this stream will have 1 bar pressure, atmospheric pressure. Now let us run the simulation, and here we have got the first warning of our simulation. Please note the warning. Okay, this is the first warning for the simulation. Let us examine why we are getting this warning. Here we are having 1 bar pressure. What is the condenser pressure of this? Check. The condenser pressure is 1.95 bar. So essentially we are saying that our feed pressure is 1 bar and condenser pressure is 1.95 bar, which cannot happen. I mean, unless we use some kind of pump or something, it cannot happen that way. Aspen is doing the calculation as per the information it is given to it, but it is giving you the warning also that unless you fix this warning, your design may be wrong. So we go back to 2 bar pressure and run the simulation. Okay, now we shall see our last task, that is change in reflux ratio in the distillation column. Okay, so let us check the distillation column. Say take this distillation column. Here our reflux ratio is 5. Okay, and suppose we reduce the reflux ratio to 3. So if your reflux ratio is decreased, distillate quality composition should be decreased, right? But if we need to keep the distillate composition intact, then we need to increase the molar enthalpy of the reboiler, right? So that is the logical conclusion. Right now the reboiler output results, what is the molar enthalpy? It is 358 calorie per mole. So this much of enthalpy is needed, or if we decrease the reflux ratio to 3, then the logical conclusion is the molar enthalpy of this stream should increase. Okay, so this one should increase, 358.3 should go higher. Let us see whether it happens, and if it happens, then to what extent. So we run simulation now. Simulation run. Now it becomes 364. Molar enthalpy 364. From 358 to 364. So molar enthalpy increased. Okay. So the opposite thing will happen if the molar enthalpy is, the distillate, the reflux ratio is increased. So the opposite thing happens with instead of 5, if it is 7, then if we run it and check 7, stream number 7 results from 358, it decreases to 354. This is what is expected. Okay, so if we increase the reflux ratio, then the molar enthalpy of bottom flow rate will decrease. So this is the conclusion of our this small exercise on hydrocarbon treatment. So we have developed the model of hydrocarbon treatment method in the Aspen simulation domain, and we have run the simulation, we have analyzed the results, and we have done a few case studies on that. Okay, thank you.